Okay, so our next speaker is Peter Müller, and he will be talking about the population finding designs of non-parametric Bayesian, not surprising, response model.
Thank you. I really don't have that much left. Can you hear me? Is it on? I don't have that much left to say after Vlad. Thank you for the chance to present here. I really appreciate it, and thanks for staying here so late. I want to tell you about just one possible way of implementing kind of the scheme that Vlad talked you through here. What you see there at the bottom is data for a trial that's actually currently going on at MD Anderson. This is a trial, this is a study for targeted therapy for metastatic cancer patients. There's two treatments. The first column shows you TT for targeted therapy, S for standard of care, enrolling across different diseases like different kinds of cancers. Outcome is progression-free survival. And then the mess starts because there's like 8 different molecular aberrations, 8 different mutations that are being recorded. And the whole intention is to try to find for some patient subpopulations characterized by some of these mutations, perhaps some of them who are better off with targeted therapy than with standard of care. And one of the aims of this trial is to identify a winning subpopulation that in some sense might most benefit from targeted therapy to take forward into a following trial. All of this is like a phase 2 trial to find the optimal population for a future trial. So we don't have to obsess about controlling type 1 error. We can do anything scientifically reasonable. This is joint work with Yanxin Xu. Sorry, I didn't. I meant it actually serious. Like anything sensible will do. This joint work with Yanxin Xu, who is now at Johns Hopkins, Ritan Mitra at Louisville, Don Barry and Leo Zimborito at MD Anderson. I don't have that much to tell you, so please feel free to interrupt me as we go along. Yeah, you don't have to keep your questions till the end. When I said the treatment is targeted therapy versus standard of care, that was of course a gross simplification. Those are like 2 bags of treatments because depending on what your mutations are, depending on what the disease is and everything, you might be eligible for different targeted therapy. And the standard of care obviously also depends on the disease, one would hope. The primary goal of this study is to determine whether targeted therapy works or not. We'll not talk about that at all. In the upcoming discussion, I want to focus on the secondary objective, namely finding the winning subpopulation of patients for whom who might most benefit from targeted therapy, and where it might be realistic to, where you would advise to start the following trial. We'll also use the inference as we go along. We'll use that inference for adaptive treatment allocation. We can preferentially allocate certain patients to certain treatments. We do so because obviously this is a very heterogeneous patient population because we essentially take patients across all diseases at MD Anderson, so cancers. And there's the notion that different treatments are likely to be effective in different subpopulations. There was one more subtlety that I should have pointed out on the first slide. Did you see when I showed you the data, there were some zeros and some ones for the mutations. There were many NAs. Those NAs don't mean missing data. That simply means the particular mutation might be pointless to record for a patient in that disease. So we have, almost as a footnote, but kind of a curious one that tickled me. We have a very simple but challenging problem. We need to do survival regression for progression-free survival on the basis of a covariate vector that will vary by patient. Like treating those missing mutations as missing data and imputing them would be borderline crazy because it might not make sense. Yeah. So in plain English, it's very easy to say on the basis of the available mutations, you have to make a judgment about progression-free survival. It's kind of funny that there's no easy method to do that, I think. Yeah. Like a clinician can do it and we can't do it. It's a little bit embarrassing. Because a clinician could judge on the basis of the available data and make a judgment, yeah? And so there should be a way to formalize that. We'll need that because in the upcoming discussion, we'll have some underlying probability models. We have to at least assume there's an underlying probability model, which shall take the form of a survival regression because the outcome is progression-free survival. The covariates are baseline covariates, treatment, disease, that's okay. But also, critically, it was actually 8 different mutations. And it doesn't make sense to impute the missing ones, yeah? It's kind of a footnote, but it was a curious one that this is such a simple question, and I didn't know any standard method to deal with that, like regression with a variable dimension covariate vector would seem to be a very basic question. This is just showing you related data from an observational study. Just making a point, it could make a huge difference, targeted therapy. We shall take a Bayesian perspective, as Vlad already advertised, going through this. So essentially, the method that I'll talk you through now will be a variation of model-based Bayesian subgroup analysis with a very well-specified purpose. Whenever you do subgroup analysis, you typically have in mind some stylized version of identifying an eligible population for a future trial or marketing exercise or whatever. Here it is a very specific one. We actually want to identify the winning subpopulation to move on with. Standard methods for subgroup analysis under a model-based Bayesian paradigm, kind of a standard thing to do is to write down a survival regression, in our case the outcome being event time. Write down a survival regression that includes an interaction of treatments and covariates. Then significant coefficients of those interactions essentially determine subgroups, right? And as has been just about pointed out, that's hopeless when you have many potential subgroups because multiplicity shall kill you. There's an interesting line of models that are based on tree-based methods. I liked it very much because it's very much in the spirit of identifying a subpopulation. Can you imagine a card-type tree on the covariate space? Like first you divide the covariate space into left and right on the basis of one covariate, then maybe you do another division on another dimension on the basis of another covariate, and that way you very quickly get like, I think there's a painter by name Mondrian who paints these like little rectangles. That way you quickly get like Mondrian paintings, yeah? And the boxes in that Mondrian painting, those are your subgroups then. There is some work by Foster, Taylor, and Ruberg, and I believe there's a 2012 paper by, there's a currently reviewed paper by Ruberg, Taylor, and others that goes further on that method. Some authors consider subgroup analysis as a formal problem of model selection because you're trying to identify a model with interactions out of a large family of possible models. That point of view is taken in Berger, Wang, and Chen, and others. In the upcoming few slides, I want to talk you through another approach, which is very simple. There's nothing difficult is going to happen. I want to talk you through a way of approaching that problem as a decision problem. That will have two important advantages. One advantage is, as I go along now, watch me, like what you should really see is what you don't see. We'll be able to talk, it's important, we'll be able to talk about the decision, we'll be able to talk about the solution without reference to a particular probability model. That's a fundamentally right way of proceeding, isn't it? Like we should be able to say what different things are worth and what we want to do with it before you know exactly what is the underlying probability model. We have to assume that there is a probability model, otherwise we cannot talk about the required expectations and probabilities, but we don't need to know what exactly it is. And the other advantage is, Vlad was already hinting at that, there's really, you have to trade off competing goals. You were talking about size of the subpopulation, remember, like his 30% and 60% versus size of the enhanced treatment effect. You obviously want a subgroup, you want to identify a subgroup with an enhanced treatment effect relative to the overall population that's as big as possible. I would add to that maybe as a third one, you want to have a subpopulation that's parsimoniously described, like it has to fit on half a PowerPoint slide, otherwise nobody will believe you, yeah? Like when you write down a complicated card tree, you could come up with like high order interactions. It's just implausible, yeah? Besides communication. So can you see how you quickly arrive, I essentially just talked to you now through my utility function, yeah? You quickly arrive at a criterion that you might want to use to select your subgroup. And I'll just talk you now through the details. One more important thing is when you think about it as a decision problem, sloppily speaking, you don't have to adjust for multiplicities. Same thing in different words. Posterior probabilities are automatically adjusted for multiplicities. You might have heard it before. That sentence is half true. Yeah? The sentence is correct in the sense the probabilities are adjusted because probability calculus is kind of correct. Yeah? But adjusting the probabilities, of course, doesn't yet tell you how to use them. So it's only half true. Yeah? And how to use them, that's what we shall specify by writing down our criterion or writing down our utility function, and that's where we explicitly trade off the competing goals. You have to do it sometimes down the line. Like if you start with the data in some problem, somewhere along the line, until you come up with a solution, you have to somewhere do some trade-off of your competing goals. I think there's something honest and clean about spelling it out and talking about it. Yeah. I have to make so much blah blah because I don't have that much to tell you. Yeah. So I'll describe the solution. I'll need some minimum. This is semi-serious, yeah. I'll describe the solution of the decision problem. I just need some minimal notation. Let's denote with y sub I the outcome. In our case, progression-free survival. We'll actually use log event times just to avoid these tedious constraints to non-negative event times. I'll use xi for the covariate vector. So for the ith patient, the covariate vector is xi1 for xip, including in particular an indicator for the treatment selection, the disease, that's categorical, and then an 8-dimensional binary vector for recording the mutations. So that's my covariate vector. And then when you want to actually talk about the optimal decision, we have to start out by introducing notation for the actions. Or same thing in different words. We have to explicitly state the action set. What kind of choices do we consider? Our actions are of the following type. We identify a subset of covariates. That subset of covariates is likely to be an indicator for the disease, and perhaps selecting one or at most two mutations to describe the winning subpopulation. We don't believe it's plausible to have interactions of more than two mutations. It's just difficult to justify. So cap I here, which is a subset of our covariates 1 through p. Cap I is just a subset of covariates that are used to characterize the subpopulation. And selecting the covariates, I have to still tell you which levels I want. For example, we'll always want to select the disease. We might want to select the disease. I have to tell you which disease, yeah, like which cancer. Then the recommended subpopulation would be a statement like, I can't resist, I have to use this new pointing device. It actually works better than these pointers, yeah. Then the solution would be of this nature, right? I would report that for some of the covariates, I want to have this disease, and I want to have this particular mutation present, for example. So this is where we are headed to. And we should be able now to describe the decision, to talk about the optimal report here, separate from inference, not totally separate, because in identifying my winning action, in identifying my proposed subpopulation, I'll take expectations of my criterion. So that's with reference to a probability model. But I don't have to talk about inference for the parameters or selecting interactions, which frees you from a whole tedious luggage that you really don't need to make that decision. It kind of separates the issue of statistical significance versus clinical relevance or relevance for marketing or whatever you want to focus on. And that has a couple of advantages. In particular, this will allow me to talk about variable numbers of covariates. Or I'll simply brutally assume that my probability model does allow for variable number of covariates, and then it better deliver. Yeah? If we have time, I'll show you in the end the particular probability model that we used because I actually like it. So I have to now formally state my utility function. I already talked you through it in plain English. I want to have a high enhanced treatment effect. That's the red thing. Since we have here event times, I shall formalize it in terms of log hazard ratio. I want to have a large size of the identified subpopulation. For the size of the subpopulation, we'll simply use as a proxy the number of patients who would fall into that subpopulation in an observational study that we already have. It's equivalent to using the empirical distribution from that database as my estimate for the covariates for the patients that we shall accrue in future. Actually, the study is running already. And I want to have a parsimonious description with as few covariates as possible. So I think we can probably all agree about the red, the brown, and the orange. The next line we might not all agree about. Yeah, I have to now, of course, I have to commit to a specific formula for my criterion. Yeah, and that's a little bit arbitrary. In plain English, on a logarithmic scale, I'm writing down a linear combination of the red, the brown, and the yellow. That's all I did. The red here is my enhanced treatment effect, where I want to have, for a positive utility, I want to have at least an enhanced treatment effect of beta. Otherwise, I'm not going to go after that. N of A is just the size of that subpopulation as estimated by the available observational data. Cardinality of cap I, remember cap I was the subset of covariates that I used to characterize my subgroup. So this is just one way of specifying a penalty for lack of parsimony, because that thing goes in a denominator, or it comes with a negative coefficient in the logarithm. Quite typical for these kinds of problems. When it comes down to formalizing my criterion, do you see there's like a couple of slightly arbitrary coefficients that I sneak in? We'll do the usual process. If you are a fundamentalist, hardcore Bayesian, you would say rational decision maker acts as if he or she were blah, 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 and you can elicit the utilities and find your alpha, beta, and gamma. That's beautiful concept, but of course crazy to do in practice. Yeah. Because there's not only one decision maker, there's multiple stakeholders to start with, and not all of them are quantitatively literate. Not everyone is comfortable with probability calculus. So in what's coming up, I will do the usual process. I will evaluate frequentist operating characteristics, and then to achieve desired levels of those, we shall change our utility function, our criterion a little bit. That's essentially it. So this is my criterion for selecting a good subpopulation. I just formalized what Vlad said before. Yeah, it's exactly what he said. He wants to have a high effect, and he doesn't want to have too small a subpopulation. You didn't say that one, but you might agree. Yeah. Sorry.
In my case, it was 3.
Oh, so that was fixed. Yeah. So what you would simply do is you would now select, you would now report the subpopulation with the highest criterion. That's the winner. Of course, you can't do that, right? Because the red thing is kind of unknown, right? The red thing is the enhanced treatment effect for the reported subpopulation. You don't know it. If you knew that, it would be unethical to run a study in the first place. So what you have to do, of course, is you have to then take the expectation of that criterion with respect to the relevant probability distribution. In our case, that's the posterior distribution. And at this moment, I already sneaked in theta, where theta is simply the parameters that index our probability model, whatever it be. I don't have to know what exactly it is, but there are some unknown parameters. And then what I have to do is I have to take the expectation of that criterion with respect to this probability model, and the winner, the subpopulation that we recommend for future study, is the one that maximizes the utility in expectation. And in principle, that's it, because that's the base rule for the optimal subpopulation. Jeremy Taylor and collaborators use some very similar criteria. They define something which they call the enhanced treatment effect, and on the basis of that, they find the winning subgroup. They stop short of like a formal decision theoretic notion, but that's essentially what they do. I want to still talk you through two more things. I'm going to talk you briefly through the probability model that we use. It's very simple. I could summarize it in a few sentences in plain English and then show you the details. And then I want to show you like some simulation results of how you put things into practice. So for the probability model, really all what we need is the notation y for the outcome and x for the covariates. We shall do the following thing. We'll construct so this is kind of a side topic. Now we quickly construct a probability model that we can plug into the previous slides. We'll construct a non-parametric survival regression that allows for variable dimension covariates, because I surely do not want to impute these missing mutations, by the following construction. I'll introduce a random partition of my patients, like I will cluster patients, that has the following huge advantage. With respect to the random partition, I can formalize the notion of a future patient joining one of the current clusters with certain probabilities on the basis of, and that's the important issue, I can do it on the basis of the covariates that I happen to know. Covariates you don't know, you simply don't include. Yeah? Like Vlad and me, we have some common preferences in terms of attending conferences. We just met at another conference. On the basis of this covariate, we cluster together. Boy, there are many other things that Vlad and me might not agree upon. I don't know them, yeah? So I don't use them for that statement. And I owe you a drink or two for all the advertisements, so maybe I can find out more about the remaining covariates. So I'll introduce a random partition model for my patients based on covariates that will allow me then the following construction for the non-parametric survival regression. For a future patient, I just think about the posterior predictive probability of the future patient joining one of the existing clusters. Conditional on joining a particular cluster, I predict your survival. Sorry, I predict your progression-free survival. That's it. And everything will happen in the context of well-defined probability models. There's a whole little cottage industry of probability models for random partitions. It's not mainstream, but it's not difficult. That's exactly what we'll use. Yeah. I'll write down details. It's not rocket science. In proceeding like this, that will allow me to proceed with variable dimension covariate vectors. There's another thing. In doing so, I can only go after classes of patients that are homogeneous in some combinations of covariates that were actually observed. I will never get into the temptation of extrapolating to interactions of covariates that were never observed. It won't happen, because you can only talk about classes of patients that were actually recorded. Yeah? I'll quickly describe a random partition model. It's not difficult, because if a cluster arrangement of your patients is the random quantity of interest, it's an awkward space, because there's awfully many possible partitions of your patients, right? If you have n patients, there's awfully many possible ways of clustering these patients. But the good news is it's only finitely many, right? Which means in plain text, you can write down just about anything as long as it's non-negative. You can always normalize, because there's only finitely many possible partitions, and you have a valid probability model. In particular, I'll use a variation of a family of probability models for random partitions that are known as PPM, product partition models. Details coming up. I promise it won't be more than like 5 minutes. Yeah. We need some notation for the cluster arrangement. We need notation for the partition. It's convenient sometimes to define a partition by way of cluster membership indicators. If for each patient I tell you in which cluster the patient falls, then I have told you the clusters, right? Alternatively, I could specify the clusters as a multi-test set. I could give you like a family of subsets that better be non-overlapping and the union cover the entire space. Then that's a partition. So I'll use cluster membership indicators S1 through Sn, where n is the number of patients. To arrange my patients into a number cap J of clusters. The cap J itself is of course random itself. I'll use one more piece of notation. I'll use notation with asterisks, superstar, will denote outcomes and covariates arranged by cluster. So Yj star is the set of observed outcomes for all patients in the J cluster. Xj star is the set of covariates for all patients in the J cluster. I think that's all the notation that I need. And remind you again, in writing down, so now what I want to do is I promised you a probability model for a random partition. My partition is indexed by cluster membership indicators. So what I owe you is a probability model for the vector of cluster membership indicators for my n patients. And I already told you it's not difficult because you can put anything on the right-hand side as long as it's non-negative, right? I want to have a probability model for the random partition that's indexed by covariates. The reason why I want it is because otherwise it wouldn't be very useful for my purpose of posterior predictive inference for progression-free survival. Unless the partitions are indexed by covariates, the probability of a future patient joining any of the clusters would be the same no matter what the covariates are. They would not be a very useful prediction, yeah? It would be coherent and everything, but useless. So by a slight abuse of notation, we are putting here the x into the conditioning set, just to indicate that the expression on the right-hand side is indexed by the covariates. Many of you might know product partition models. So the black part, that is just, those are traditional probability models for random partitions. One that is particularly overused perhaps is the so-called Chinese restaurant process, or the polyion, which arises under IID sampling with a Dirichlet process prion, blah, 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 blah. Like many of you might know that if you don't know it, it's just any expression you can put here. The important thing is the red thing. We multiply with a factor that penalizes for clusters that are heterogeneous in the covariates, or same thing in different words, that encourages the formation of clusters that are homogeneous in the covariates, just by increasing the probability for these partitions. So all what I owe you now is an expression for the red thing, and if you want, I give you an expression for the black thing too. So the red thing should just be some score, should be some evaluation of how similar the patients in a particular cluster are. And here is now where the rubber hits the road, or whatever is your favorite metaphor. What we do here now is we take a product over all covariates. Oops. There should be a product over all patients in the cluster. There should be a product over all I in the J cluster of some function. Whoop. I have to take back what I took back. Nothing is missing here, yeah? Product over all covariates of some function of all the observed covariates, of all the observed values for that covariate in that cluster. The important thing is in this curly brackets for this set of covariate values for this covariate in that cluster, we only include those covariates that are observed. If they're not observed for a patient, they just don't show up here, yeah? Like if I don't know a particular mutation for a particular patient, it just cannot feature in my judgment whether this cluster is homogeneous in that covariate or not. I could almost tell you anything here because anything that's non-negative works. Yeah. So this specifies my prior probability model for a random partition. For those of you who know this kind of ballgame, all what I did was I introduced a product partition model that included a factor that used the covariates, that's all. And then conditional on a particular cluster arrangement of my patients, I still have to assume a sampling model for the log progression-free survival time. I just assume now independent probability models independent across the clusters, and within each cluster independent across patients, conditional on a cluster-specific parameter. Think of the eta j as something like the mean progression-free survival for patients in that cluster. If that cluster selects all women with a particular cancer and a particular combination of the mutations, then the eta j would become the mean progression-free survival of such patients. Then in the context of this probability model, I can talk about prediction for a future patient. You can do that in two steps. You can first evaluate the posterior predictive probability of the future patient joining one of the existing clusters, and then conditional on that, I would predict for that future patient the progression-free survival that is based on that eta j. That's all. In the course of that description, I introduced a couple of random quantities. The random partition is a random quantity. Those eta j's are latent random quantities. At the end of the day, you have to marginalize them all out. We do that when we do, if we base all of this on Bayesian posterior inference, we would do that with the customary posterior Markov chain Monte Carlo simulation. Like each time you think about, you impute one possible cluster arrangement, one possible set of the eta j's. On the basis of that, you do your prediction. Then you update everything, and at the end of the day, you average. And that's it. That's the description of the probability model. It was a little fast, but I really did not cheat you out of many details. Yeah, it was based on a random partition using a product partition model indexed by covariates. The advantage of that was I only used the covariates. I only had to use the covariates that I knew. I did not have to. Do you remember our former defense secretary in the US who talked about known unknowns and unknown unknowns? So we only have to use known. Would he have said known knowns? Anyway, so in the end you get coherent posterior predictive inference for progression-free survival for a future patient indexed by the new patient's covariates. So in other words, you get a non-parametric survival regression. On the basis of that, we can now carry out our desired inference. I could now evaluate the expected utility for all possible subpopulations and look for the winning one, and that's the one that we report. And there was still that subtle issue that we had these arbitrary coefficients in the utility function. To fix those, we want to carry out some simulation. Carrying out simulation, we do the usual process. So you fix like some possible scenarios. You see here 10 different scenarios, including in red in the second line. There's a scenario that I would describe as the null scenario, when nobody has no effect at all. Nobody shows no response at all to the treatment. Means progression-free survival with or without treatment is the same. In green is something like the overall alternative hypothesis. There are no subgroup effects, but there is an overall effect of 0.3 in this case. And in between, you see situations where there might be an overall effect, a moderate overall effect, and then patients who carry the KRAS mutation, who are colon cancer patients, and who receive targeted therapy, set here as an indicator for the treatment, they have an additional treatment effect of 0.4. In other words, this would describe a very attractive subpopulation in this simulation truth. Yeah? And same way, under the other scenarios, there's alternative simulation truths, and then we carry out massive simulations. So what we do is, in each simulation, We fix an assumed simulation truth, like each line defines the simulation truth. Under that truth by simulation, we carry out massive repeat simulation, like we massively many times we simulate what might happen in a hypothetical realization of the trial, and then averaging what might happen, we get bona fide frequentist probabilities on the repeat simulation. And then we record these probabilities. I'll show you what we get in the end, but the true process, of course, is you first start out with some set of coefficients. You see the frequentist summaries. They typically look awful. Then you adjust things until you get what you want. There's one more slight problem there. On the next slide, I want to tell you now about type 1 error and such things. Did you see that in my simulation truth, there's nothing like a well-defined null hypothesis. I have to. The simulation truth does not include a statement of what is the true subgroup. There was kind of obvious candidates, yeah, but we have to specify that somehow we just make a reasonable definition of it. Let's not bother with the details. And then we can report under this repeat simulation. There's one more subtlety. When you do hypothesis testing, there's two possible truths and two possible decisions you can make. So there's two ways of how you can screw up, right? Now, in this case, there's not only two possible truths. There's like the overall null, there's the overall alternative, and many shades of gray in between. So there's many different ways of how you can do it wrong. So there's like a large number of ways of, there's a large number of frequentist errors that you might want to record. Here's what we will report. We'll report, so these are all probabilities under repeat simulation. So these are all frequentist probabilities under repeated simulation of hypothetical trial realizations under the proposed approach. I just use this notation as a mnemonic for behind the bar is the simulation truth. So if I simulate under that was indicated in red on the previous slide, if I simulate under an assumed scenario where nothing works, and if my recommended subpopulation is anything but the empty set, that's an error, right? That's what we call type 1 error. True positive rate is if behind the bar, the H1 means I simulate under assuming that there's only an overall effect and no subgroup effects. And if I correctly report as the winning subpopulation the entire population, we call it the true positive rate. False subgroup rate is if the truth does not include a particular subgroup, and you have to specify what it means to include a subgroup. That was the previous slide that I jumped over. But I recommend a particular subgroup, then that is a false subgroup rate, right? And in that fashion, you can report frequentist summaries of the entire process, or same thing, just in a table, right? The truth can be either the two extremes, nothing or all, or it can be many things in between, right? My decision can be to report no winning subpopulation, to recommend against any following trial, or it can be to recommend the following trial with the entire patient population, or it can be anything in between. And depending on what the truth is and what you recommend, you get like different error rates. And that's exactly what we did. And then you get results like this. Disclosure. This, of course, is what you get after an iterative process of seeing summaries, adjusting your rates, and proceeding. And we adjusted not only the parameters, we even adjusted our utility function to achieve what we wanted here, yeah? Which is fairly typical, because when I wrote down the utility function, when I wrote down my criterion, in plain English, I think it was easy to justify it and defend it. The actual formalization was a bit arbitrary. So I have no problems iterating over alternative specifications until you get satisfactory rates. We also include in this particular trial, I didn't talk about that at all, but as you proceed and as you learn more about the winning subpopulations, as you learn more about different response rates for different subpopulations, you can allocate patients preferably to treatments that look favorable for the patient. This is to introduce some notion of patient-specific utility in the trial. And if you do that, then you can report how often you allocate patients to the treatment that is truly preferable for them under the simulation truth. And that actually concludes everything I wanted to tell you. We used, so this, like I talked here through a Bayesian approach to selecting the winning subpopulation. It's totally okay because this was a phase 2 trial. We are talking about some rational process to come up with a good suggestion of what to do next. In one liner was, I suggested use the Bayes rule, yeah? That's all what I did. And of course, to make that suggestion, you have to specify a utility function, and we did that. We did not have to fight with multiplicity control because the probabilities are adjusted for multiplicities. The adjustment in the decision happens by Bayes rule, like by maximizing our utility and expectation. In the end, I should still say, of course, we don't take ourselves too serious. It would be borderline crazy to take that machine that I talked you through. Then in the end, you get like a subpopulation recommendation, and to just trust it would be borderline crazy. What we really do is, in the end, we report like the 10 best winners, and then presumably you'd use some clinical judgment or alternative considerations to select a plausible one. Basic biology or clinical collaborators are great. When you show them solutions, they can always give you some reason why that has to be the case. Yeah. So if you give them, because then they start to think about possible processes. I think it's not totally irrational. Yeah. So giving them 10 choices is perhaps even better. That's all I wanted to tell you about. Thank you. No complaints at all. I told you quite a few monstrosities, but yeah.
You want to talk a little more about what you didn't talk about, the response to that, the changing the allocation probabilities? Do you have some systematic way of doing that that preserves the properties of the trial?
Yes to the subordinate clause, no to the main clause. It's not systematic what we do, yeah? But it preserves the properties of the trial because the simulation the frequently summaries that I showed you, those were under that rule. What we do is we do the usual adaptive allocation a la our colleague Peter Tal in MD Anderson does a lot of that. We do the following thing. And there's no good mathematical reason to do that. That's why I was shamefully quiet about it. Yeah. For each patient, we can evaluate the posterior predictive progression-free survival under any possible treatment assignment, and then we can suggest to allocate the treatment with a probability that's proportional, so to allocate a particular treatment with a probability that's proportional to the probability of that treatment being optimal for the patient. There's no reason why these two probabilities should have anything to do with each other, yeah? But it's not uncommon. In this particular trial, we have one more advantage. We only have to randomize targeted therapy or control. If a patient is eligible for multiple targeted therapies because he or she has multiple mutations that could be targeted, then that's not us who decided, but there is a board for that particular study, a cancer board of clinicians who make the choice. Yeah?
Peter, at some point you said about changing the utility function so you have the appropriate operating characteristics, and it was very nice under the null you have 0.05. Very reassuring. But what is the more important? That the utility function is acceptable to the your clinical colleagues on the team, or that you get 0.05?
It depends on ways.
I would like to have my cake and eat it too, yeah? Both, I think. I was being a bit sarcastic, changing a utility function. I should have said refining it. Invariably, when you write down your first shot at your criterion, you're going to write down something that's crazy in terms of the implied solution. The solution is only very implicitly determined by a utility function. It's determined by, it's the rule that maximizes an expectation, right? I think it's okay. Like if you really have a utility function that you're willing to defend, by all means you should of course use it, yeah? But typically there's like some issues of calibrating things, adding terms. It's very typical. When you just write down a utility function, then it has crazy implications. These are not like your usual inference loss. Like these are not your usual quadratic error loss function or so. You could use that if that truly were your utility, but presumably that's not at all your clinical utility. Yeah? Like this is not about learning about the subpopulations. This is about selecting the subpopulation that's best for the next trial. Another one of my favorite ones, and you know those very well, is the following one. Our utility function could be the posterior predictive probability of the next trial succeeding. And that's actually very easy to formalize because all you need is a stylized description of the following trial. Then you need the posterior predictive probability of the test statistic in that future trial falling into the rejection region. It's not so difficult actually, yeah. But that's almost that's a slightly it's almost sarcastic. Yeah? It's like you don't care at all about other things. You just want a successful future trial. Any other comments? Yeah.
In your utility, that you use the gamma and alpha. Are those two parameters possible to be played with in order to achieve good performance?
Yes, and that's what we did. Yeah. Like as Andy pointed out, once you lose your honor, life is much easier. Yeah. Don't quote you on it. Yeah? Well, like straight out of the basic paradigm, you should write down a utility function. You should stick to that. Yeah. You should only have one utility function, and that's it. The truth, of course, is the problem is way too complex to do that. So we did adjust it. It's exactly what we did adjust. Yeah.
Tell me more about the Chinese restaurants.
It's actually embarrassing because it's not particularly smart. But it's very popular. Like many of you might have heard talks about Dirichlet process, or if it's a machine learning talk, they would talk about Chinese restaurant process. Or if it's computer scientists, they might talk about the polio urn. When I had in black that C of Sj, if that particular expression is size of the Chave cluster, like cardinality of the Chave cluster, minus 1 factorial, then the black thing without the red factor, that defines a probability model for a random partition that is known as the Chinese restaurant process. It's a very embarrassing one because the metaphor comes from the following, the name comes from the following notion. Imagine a Chinese restaurant that has infinitely many large tables. If each table corresponds to a cluster, and as patients are accrued in the trial, they join one of the tables. If they join the tables with the following probabilities, imagine there's already n patients are sitting on the tables. The n plus first patient comes in. If the new patient joins one of the tables with a probability that is proportional to the number of people who already sit on the table, or goes to a new empty table with a probability that's proportional to some, we call it total mass parameter, m. If you use that rule, that defines the Chinese restaurant process. When I said it's embarrassing for the following reason. Did you notice in the description, it's a description of kind of the popular table gets more and more popular, like the rich get richer? Because the new patient joins the already popular table with a probability proportional to the number of people on the table. So actually what you get under this process, you get cluster sizes that are in expectation geometrically ordered, means they are geometrically decreasing. You would probably not expect it a priori about your subpopulations of patients. Unless you have something in mind, you might a priori think you have an unknown number of subpopulations, but they should all be of approximately comparable size. Same thing in different worlds. From a point of view of clinical usefulness, a small singleton subpopulation is totally uninteresting. To really have subpopulations that are meaningful for drug development, you want reasonable sized subpopulations. So to the extent to which it is okay to gobble up utility and prior, and you can, because in the end you anyway multiply them. You surely don't want singletons, but singletons is what you get with the Chinese restaurant process. So the Chinese restaurant process is actually a very asocial dining arrangement, yeah? Like there's the popular table with everyone, and then there's many singleton tables. And you probably don't really want that, yeah? The reason why we did it was because it's easy, yeah?
I think that's a good way to stop now. That's easy things. Thank you very much, Peter.